We left off in the middle of 3.2. Actually, we're really close to the end of it. We just have a few slides left. And we had gone through, well, let me just run through real quick a few of the things we've gone through. We've gone through some different algorithms, and remember, algorithm just means a process for doing something. We've gone through a couple of algorithms or a few algorithms for addition, and then a few more than that, algorithms for subtraction. So we had this concrete model. This is the idea of actually using some physical object to represent something. We talked about the expanded and the standard algorithm, which are very similar. The standard algorithm is just sort of a simplified way of writing the expanded algorithm. And the standard algorithm is probably the one that you've been most familiar with up until now. We talked about some more sort of inherent problems in doing that. However, it's extremely efficient. It's very quick and nice for that feature alone. We did a left to right algorithm, and we talked about how the stuff that's written on the left-hand side over here, that's not actually stuff you would really write down if a student were doing it, but that's what you should be thinking as you're working through the problem. And then we did lattice, and some of you smiled and said, ooh, I really like that. And it has a really nice feature to putting things in columns and then adding along diagonals, and we'll encounter that lattice argument one more time when we get to multiplication. And then we had scratch algorithm, and can you tell me, when do we use scratch algorithm, or when is it useful? We have lots of numbers to add together, and by lots of numbers we don't mean numbers that are large, right? We mean several items that we're adding together. So you're thinking the items in the basket at Walmart when you're going through or something like that, a bunch of items together. And then we did the subtraction algorithms. We did the concrete, expanded, and standard, and those are all pretty much the same thing as they were for addition. They're modeled in very much the same way. And we had this equal additions, and this is where we left off. We talked about equal additions algorithm. What was the whole purpose of the equal additions algorithm? What was it? No borrowing. So we're adding values to basically the second number so that it does not require us to borrow when we actually do the subtraction of it. So we added the 2 to get this up to 160 so that we didn't have to borrow from this 4 right here and this 8 to get that. We didn't have to do any borrowing. So this became 160. The contention was, though, that if we did this 2 here, we do it to the top as well. All right, equal additions. And then over here, we still run into another problem. If you stop right here, you still have to borrow, which defeats the whole point of the whole process. So we do the same thing again. We look at 160 and we say, oh, but if I add 40, then I can turn this number into 200. And then finally, when I do that and I add 40 top and bottom, I'm able to subtract no borrowing. So that's equal additions. Okay, I think that puts us where we are. So I actually said it wrong. We have more algorithms for addition than for subtraction. Sorry, there's a pen missing. Oh, there it is. Thank you. All right, so what I want to do in the rest of these is, I think it's all 3, the rest of them, 5, 4, is you see that we're going to do different algorithms how? In other bases. Why would we want to do that? Because of the other chapter. Well, we learned about other bases in the other chapter, so that was part of why we learned about the other bases, so that we got to here we could use this feature. Do you remember what we talked about when we talked about the Egyptians and the Romans and the Babylonians and all those different systems? About why we did that piece there too? Right. That's the wrong right idea, Carrie, yes. So you guys are so familiar and comfortable with base 10 that you look at those algorithms that I showed you and you say, well, of course it works that way. And that's very easy and it makes a lot of sense and it's perfectly reasonable. And if I'm explaining this to the 6-year-old, why don't they get it? I mean, it's really easy. It's really obvious. Well, you've been doing it for quite a long time. So by working in other bases, you put yourself back into that mindset of being a little bit uncomfortable with the way these operations work. That's why. Okay? So this is supposed to feel a little uncomfortable, and that's expected, and it's okay. All right? So we're all ready to be just a little bit uncomfortable as we work through some of these? Okay. So first of all, to remind yourself a little bit about other bases, we're going to start with the base 8 problem. Do you remember what the numerals are in base 8? 0 through 7, actually, right? Yep. So we'll start with 0. And in particular, just a sec. Okay, in particular, what you want to remember is there is no 8 in base 8. So whatever we name the base, we don't actually have a numeral of that value, right? Okay. So we're going to actually add 3, 4 base 8 plus 1, 7 base 8, and we have lots of methods for doing that because we just went through them, even now in the beginning of this class, of all these different methods for adding, okay? So let's use the standard algorithm first so you can see how that would work, but then we're going to do a different algorithm so that you can see how that would feel if you were working in there. Sound good? All right, so standard algorithm, the one that you are most familiar with. What you want to remember is this is all in base 8. You don't have to write yourself a note to that, but you have to be thinking about it, otherwise you're going to go adding this like it's in base 10. All right, so if you add 4 and 7 in base 10, what do you get? 11. But in doing that, you cross through the numbers 8, 9, and 10, and none of those even exist, so they don't make sense in base 8. So what you see kids doing with our base system, and what you may be thinking when you do this, is this idea of counting up to the number I got. So you know you've got 7 just because you're working with the larger one, and you know you need to add 4 to it. So what comes after 7? Think about a number line. What comes after 7 in base 8? There's no 8 in base 8. It goes back to 1, 0. Okay? So if you're thinking about what we would do if we kept going on this list, the next one would be 1, 0, and then we keep going, right? So we're going to count up, but once we got through 7, we've got to go back to, like Katie said, 1, 0. And we're going to do it 4 times, right? So after 7, we have 1, 0, 1, 1, 1, 2, 1, 3. Okay, so the number we should be getting with 7 plus 4 is 1, 3. So what do we do in our standard algorithm? Put 3 on the bottom, and we carry the 1. That's what we do. And then the next addition, this next column here, the 8th column, is really clean because it doesn't exceed 7. We just add 1 plus 3 plus 1, and we get 5. So the answer is 5, 3, base 8. Please do not forget to write down that subscript because that changes the meaning without it. So far, so good? Okay. Now I want to show you what we do with scratch addition. And I recognize that this doesn't have multiple numbers, but I want to show you how it affects the working of the problem. Okay? So we're going to do it kind of like it were scratch addition. Again, recognizing that this is not the traditional case when I told you we would use this. Okay, so you know that once you get to 10 in base 10, you scratch. Why did you do it when you got to the number 10? Because it turned into a 2-digit number. Okay? So if you're counting 4 plus 7, when do you scratch in base 8? When you get to 8. Are you with me? So as soon as you get to 8, you scratch. So you know, in other words here, that 7 plus 4 in our base 10 system is what number? It's 11, right? But 8 of those should be scratched off. I'll work this again another way in just a second with the scratch addition. But you're scratching because you got to the number 8. In fact, you know what might be helpful? Let me do it that way. Let me write it upside down from what this is. I think that might be more helpful to see it thought through that way. All right, so we have 7. When we get to 8, we scratch. That was one of the 4 numbers I added. How many more am I supposed to be adding after I've scratched? 3. So the scratch happened when I got to 8, because 8 in base 8 is a 1 and a 0. And once I get to a 2-digit number, I scratch. So I scratched when I got to the number 8, or the number 10 in base 8. There were 3 more to add after that, so I write the number 3 down below. Now, again, with scratch addition, we count up the scratches. How many scratches do I have? 1, and then we carry that number 1 over here, because I've got 1 scratch. So 1 plus 1 plus 3 is 5. Okay, so still 5, 3, base 8. So some students like to add the ones column together and then take away however many they need to in terms of 8. That's another way to do it. So let me think about it with you that way. So let's say you added 7 plus 4 in base 10, which would be the number 11. We've done this several times. So we would get 11. And 11, we want to figure out, well, what is 11 in base 8? Well, it's more than 8, so if I subtract off one of the 8s, that is 11 minus 8, what do I get? 3. So I wrote the 3 down, and because I subtracted off an 8, I carried 1 and 8 over. It's regrouping, that's all it is. You're regrouping. Once you get to 8 objects, you have to regroup them all into one long, right? Concrete object. Okay? So you can almost work with, you don't have a coin like this, but if I were in base 4, you could work with quarters, right? Once you got too many quarters, you would change it up into a doll. And that's what sort of feels good. Let's try another one. Subtraction one, right? We're going to do it with the standard algorithm first, okay? Because you guys like it, or at least you think you do. So the problem inherent in what's written is what? I can't take 7 away from 4. There's not enough there. So in the standard algorithm, we have to borrow, right? We borrow. And we take this 3, and what does the 3 become? A 2, because I borrow one of those numbers away. But in base 8, how many am I borrowing? 8. Okay. When you borrow in base 10, you borrow 10. Because what the reality is that this is the 1s column, and this is the 8s column. And if we went one more over, it would be the 64s column, right? 8 times 8 is the reason we have the hundreds column. So when I borrow this 1 from the number 3 to turn it into a 2, I borrow 8. So now I have 8 little individual objects. Can you picture it? The little cubes. You've got 8 cubes on the table, plus your original 4 cubes. So how many little cubes do you have floating around on the table? You have 12. And so it makes good sense to actually mark this out and put 12. And you can write the 12. This is not the number 1, 2. This is 12. I have 12 little bitty objects all sitting around here. And I can do the subtraction then with what you know about 12 minus 7. And 12 minus 7 is 5. Thank you. And then I've got 2 minus 1 to give me 1. And this is again in base 8. Yes. Okay, so in our base 10, what we would see happen if I took this 3 and turned it into a 2 is that I would have borrowed 10. And the reason I would have borrowed 10 is because it is in base 10. Each column is 10 times as much as the one before. Okay? And so in our base system, we would have taken those 10 blocks, let's say, and we would have had the original 4 blocks. 10 blocks plus 4 blocks is 14 blocks. So the 4 would have become a 14. But in base 8, when I borrow, I don't borrow 10, I only borrow 8. It would be like having a long piece, but in base 8, that long piece is only 8 blocks, and breaking them all into little blocks, like breaking them apart. So now I have 8 individual blocks plus the original 4 for 12 blocks. Okay? Yes, Cindy?
So, like, what if it would have been a 1 instead of a 4? So would it have been 9?
Yes, you would have written 9. Because remember, what I'm writing above here is not a numeral in base 8. We don't do it in our system either, right? Because if I'd gotten like a 12, we would have written down 12. I mean, we don't write it in a way that is a single digit necessarily. So we're just going to write it in our base 10 numerical thinking for it, and that's fine.
Okay.
Yeah.
What if it would have turned out like the number that we've gotten if it was over 8? Like instead of 5 was
It can't do a subtraction. That can never happen, because if it did, then that would have meant you would have been needed to borrow to do it.
Oh, okay.
Yeah. Good question. All right, we're going to do this with, it looks like what I have written down next is that equal additions algorithm, which I quite like. So 1/7 is actually the biggest 1-something number you can get in base 8, right? Because there is no 1/8 in base 8, right? So if I were to add 1 to 1/7, what would it become? 2-0. The equal addition says if I add 1 to the 1/7 on bottom, what else do I have to do? Add it to the top. So what is 3-4 plus 1? 3-5. And if you subtract, what do you get? 15 or 1-5, right? actually think that's a lot easier in this particular problem.
How is the 20 or the 20?
Okay, so Angela, you were the one who said it. Do you feel comfortable answering where did the 20 come from?
Well, it's like whenever you're going from, like when you get to 9, you go to 10, which is the first two numerals. And so whenever you're going from in base 8, like there's no 8, and so instead of 18, you have to go back to the original number, which is 20. Like you would go to 10.
Okay, so like if we were listing out all the numbers, at the point when we get to 16, 17, there isn't a 18 because there's no 8. So that means I have to increase the first digit to a 2, and the last digit becomes a 0. It's much like when we get to the number 19 in base 10. We don't have another number to change that 9 to, except for to use 2 more another place to do it.
Just like when you're done.
Exactly, and that's what you were getting at when you got to the end of 9. Yes, right. Okay, so this is equal additions. What do you think?
So if the 17 was a 27, the 20 would be a 3.
Yes, if it had said 2 7 instead of 1 7, then the 2 7 would have become a 3 0. That's right. Any other questions on that one?
So if it's 16, 17,
It goes 1 6 1 7 2 0. Yes. Yeah, like if we were to list out like a number line picture of it, yes. We go 1 6 1 7 2 0.
So if we get confused, the best answer is just to write out a number line.
You can, yeah, if that helps you to see it, think about it that way. And it will help some of your kids to do it that way too. Because I had these moments, I think it was last fall, where my son was doing, and he's still learning a little bit, he's farther along than he was a year ago, mind you. He was doing counting, and he did this, he did 34, 35, 36, 37, 38, 39, 30, 10. That's this. I mean, that's what he's doing. The next number is 30, 10, except that what we do is we regroup and we call it something different. We call it 40. Okay, so that's what you're doing here. You're regrouping, but you're regrouping when you get to an 8 instead. Again, putting yourself back in that position of the child who says 30, 10. Why can't I have 30, 10? Right? It's the convention we use. That's why you can't. And that's the only reason you can't, because that's the convention that we have created for using our number system. All right. Is there one more? Might be 2 more. 2 more. All right, we're going to do the same kind of thing now with base 3. All right, so you're far too comfortable now with base 8. Somebody tell me, what are the numerals in base 3? It's not very many numerals to work with, is it? And if I were working on a number line, I'd very quickly have to turn this into a 2-digit number, wouldn't I? If I were counting objects and so forth. All right, so first thing we're going to do is we're going to add. We're going to add 1 2 1 2 base 3 plus 1 1 2 base 3. And I'm first going to do it with the standard algorithm, because you guys think you like it. But we'll do a fun one next. Okay, so we start on the right-hand side, and we would say 2 plus 2 in base 10 is 4. There's no 4 in base 3. So what is 2 plus 2 in base 10? It's 1 1. And if you need to think about it with a number line, you can. Or if you need to think about it writing out, more digits, you can. What comes after 2 0? Sorry, what comes after 2? Yeah, 1 0. 2 0 would be next, yeah. You don't have to go very far in writing these out, okay? Because you're going to run out of what you need to add together pretty quickly. All right, so then what happens when I have 1 plus 1 plus 1? That's 1 0, isn't it? Because it would have been 3. There's no 3 in base 3. So this is 1 0, so you write down a 0 and you carry a 1. 1 plus 2 is, 1 plus 2 plus 1. My numbers aren't lined up very well. I'm right here. That's 1 1, so I'm going to write down my 1 and carry a 1. And then I have a 2, and this is base 3.
Can we write the number 3 or do you want us to write the word?
If you write the number 3, it needs to be in parentheses, so it doesn't end up being confused with the numbers that are already there. So to set it apart, your book uses the whole word to do that. But some books will use it parentheses, they'll do it like this. As a subscript, but in parentheses. If it's not in parentheses, it starts to look very fishy and it starts to look like it's part of the actual division. Yes, Hannah.
So when you're adding, like when you added the 2 and 2 and so you get 4, so why wouldn't that one be 10? Because 10 is the fourth.
Oh, okay, so when I add 2, I'm starting with 2 and I'm going 2 further on the number
Oh,
line.
okay.
So you're actually at 11, Yeah.
That makes more
or at
sense.
1, 1. Yeah. All right, so the next one I'm going to do, which one do you think you might want to try? Lattice, that's the one I was going to do. All right, so we're going to do a lattice. Oops. Let me write our numbers down first. I have 1, 2, 1, 2, 1, 1, 2. Okay, so for lattice, we're going to make a box. We need each of the place values that we're adding together to have a broken piece of that box below. So there's 4 digits in the first number, so there'll be 4 digits in my box. And then I need to split my box up into diagonals. So they go like this. All right, so then we're going to add, and I get to do the same 2 plus 2 I did before. So it's still the number 1, 1. Remember 1, 1? So I put 1 here and 1 here. Now, the nice thing is that on the next one when I add, I don't actually exceed 3. I don't get to 3. So here I have 1 plus 1, which is actually just 2. So I have fewer times when I exceed the 3 that I'm needing to change my base stuff around. What about 2 plus 1? That's 1, 0. So here's a 1 and there's the 0. And then this number 1 comes straight down. And then we're going to add along the diagonals. So we start with the bottom right diagonal, and that's number 1. Okay. The next diagonal has a 1 plus a 2, which is 1, 0. So we write down the 0 and we carry the 1. And the 1 carries over to the next diagonal column, which is here. Then I have 1 plus 0, which is 1, and 1 plus 1, which is 2. So my solution didn't match. Oh, that's good. 2, 1, 0, 1, base 3. Okay. Last one. Subtraction, still base 3. We're going to do this in our number, or our standard algorithm first. And at least one feature is nice, because with the standard algorithm subtraction, what do I get to do on the first step in the ones place? I can just subtract, right? There's nothing upstairs that's smaller than downstairs, none of that's going on. So I can actually do 2 minus 0, and I've got 2. No borrowing. But the next one runs into a problem, and actually, Nicole, this is very similar to the question you asked me after class last time, but in base 10, right? So the problem is that both of the next 2 placeholders have zeros on top, which means I can't borrow from the 3rd place for the 2nd place, because there's nothing there to borrow. I just can't. It's not possible. So I actually have to go all the way over to the 4th digit, which is actually the 8th place, or well, no, it's 27th place in this number system because I'm in base 3. But the 4th digit, where we normally have the thousands, right? And this 1 has to become 1 less, so it's becoming 0. But this is in base 3. So in base 3, when you borrow from one column over, how many do you borrow? 3. Whatever base system is, that's what you're borrowing. You're taking whatever that block or that unit or that flat or whatever the object was, and you're breaking it into pieces. But the pieces you can break it into have to be within the base system you're working in. So I'm going to borrow 3. So this 0 actually becomes 3. And that would be great if I had already been able to subtract the column prior to that, but I wasn't able to do that. Now that I have 3 in that 3rd column, I'm able to borrow from it. Right? So the 3 will actually become a 2. And when I borrow, I borrowed 3, because I'm in base 3. So this 0 becomes a 3. So you've got this multiple borrowing. And this happens in kids' textbooks and stuff. This happens, right? This is exactly what Nicole was asking me a question about in base 10, where somebody was having to borrow multiple times. And why in the world did something become a 9 out of 10? And where was that happening, and how would I explain that? Well, you can explain it because what you're really doing is you're breaking something into the number of pieces in that base 10. Now you can subtract, because all the borrowing is done, right? Okay, so 3 minus 1, 2. 2 minus 1, 1, and then of course I have 0 over here because there's nothing left. This is 1, 2, 2, base 3. So it's only in the borrowing that the base system comes into play. After that, I'm able to subtract just like you're able to subtract in base 10. Okay, we're going to do equal additions with this next. So I have 1, 0, 0, 2, and then I have 1, 1, 0. And as we established, I would have to borrow in order for this to work. The goal with equal additions is that I don't want to borrow. Now, the problem is not in the ones place here, because that's a 0. I didn't have to borrow there anyway. But I do have to borrow in the second place over, right? It's the 3's place in this problem. So what would I have to add to the 1 to turn it into a 0? 2. And I'm not going to add just 2 because that would affect the number 0. What should I add? I should add 2, 0. Okay, so it's going to look a little bit different. So on the top, that's easy enough. That becomes 1, 0, 2, 2. On the bottom, what happens when I take 1, 1, 0 and I add 2, 0 to it? Well, the last 0 stayed put. But what happens when I add 2 and 1? What do I get?
1, 0.
I get 1, 0. So I get the 0, and then I get a 1 that gets added to the 1 in the next column over. So this is now 2, 0, 0. Again, if you're struggling, think about writing it out. What would come after 1, 1, 0? Well, it would be 1, 1, 1, and then 1, 1, 2, and then 1, 1, 3, 1, 2, 0. And that's equivalent to what's happening here when I've added the 2, is that I've added 3 of these numbers because I'm in base 3. Okay. I'm sorry, and I have to keep going to get to the 2, 0. But, all right, so here's the problem. I still have to borrow, don't I? But just once, right? But the whole goal of equal additions is that I don't have to borrow. I don't want to borrow. If I'm using equal additions, the goal is no borrowing. So what would I need to add to 2, 0, 0? 1, 0, 0. And if you want to think about it, 200 plus 100 is 300, and once I get to 300, I don't have a 3. I mean, that's what's really happening here, right? Once I got to 30, I don't have a 3. So I have to have one more place value to do that. Okay. So if I add 1, 0, 0 on top, that's easy, because the number in that placeholder is a 0 anyway, so this is 1, 1, 2, 2. On bottom, what does 2, 0, 0 become?
1, 0, 0.
Right, 1, 0, 0, 0. And if you subtract 1, 1, 2, 2 minus 1, 0, 0, 0, what do you get? Yeah, 1, 2, 2 base 3.
Okay,
Yes.
how do you know what to add? Like, how did you know to add to 1?
Okay, so can someone answer that for Carrie? How did we know that we wanted to add 20 or that we wanted to add 100?
I have a question though. Can't you get the answer without doing 100? Can't you just start subtracting there and you'll get 100?
But in order to do it, you would have to borrow. That's the whole point of equal additions. Equal additions is a method that eliminates the need to borrow.
I know, but couldn't you stop after you added the 20?
You could, but then you wouldn't be using the equal additions
Oh.
algorithm. Yes. It's an algorithm issue. It's not an issue of can I or can't I, because you certainly could.
Okay.
We could have not done any of the adding on, but then we wouldn't be doing equal additions. So I'm just showing you what equal additions would look like if you did the problem. Yeah. Okay, did Hannah, were you able to explain that? Or who was talking to Karen?
Yeah.
Hannah and Hannah were talking. The goal is to get everything, well, not necessarily it has to be, but yes, typically speaking, you're going to add things to get zeros. So in base 10, we would, you know what the numbers are to get to the number 10. And what do you have to add to 6 to get to 10? 4, right? Because 6 plus 4 is 10. Well, the same thing works with any other base. You just have to think more carefully about what those numbers are because you're trying to get to the number of the base. So the reason we added the 1 or the 2 in each of those cases was because our goal was to get to base 3 because we're working at base 3. All right, let me put up the slide with the homework. Jot that down. know it says we're supposed to go on to 3.3 today, but we do it in 5 minutes worth. I'm not sure that's worth our time. So we're going to pause here today. 3.2 is finished. We'll start 3.3 on Friday. You guys got new groups last time. Some of you weren't here, so you don't know who you're with or potentially not. So I'm going to go through the group assignment one more time. Has everybody got this written down? Almost? Okay.